Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through a chain of cosmic discoveries, from the hidden fields inside matter to the old light of the universe itself. For now, imagine the night sky not as a ceiling, but as a quiet library. Every star is a small lamp over a page. Every galaxy is a shelf so distant that its story arrives late, softened by the long travel of light. In that library, science does not begin with certainty. It begins with a question that refuses to disappear. Why does matter have mass? Why does time bend? Why do galaxies turn as if something unseen is holding them together? Why does the universe look as if it once grew from a hotter, denser state? A discovery is often pictured as a sudden flash, but the real process is usually slower and calmer. It is a pattern noticed in the dark. It is a mathematical possibility left waiting for evidence. It is a detector beneath a mountain, a telescope above the atmosphere, or a particle collider listening for something that vanishes almost as soon as it appears. One of the most elegant examples begins with the simple fact that the world has weight. A stone sits in your hand. A planet holds an atmosphere. A star gathers itself into a glowing sphere. Underneath those ordinary experiences is a subtler question. Why do some fundamental particles move through the universe as if they carry mass at all? The answer that emerged from modern physics is the Higgs field. It is not a tiny object hidden inside matter, and it is not a magical substance sprinkled through space. It is better imagined as a quiet condition of the universe, a field present everywhere, shaping the behavior of certain particles as they move. The Higgs boson is the ripple associated with that field. When physicists found evidence for it at the Large Hadron Collider, they were not discovering an everyday ingredient like a new mineral or a new planet. They were catching a brief signature of a deeper structure that had been predicted by theory decades earlier. The nickname sometimes attached to the Higgs boson can make the discovery sound mystical, but the science is more precise and more beautiful than the nickname. The Higgs field helps explain why the carriers of the weak nuclear force have mass, and how the mathematical structure of particle physics can remain coherent while the world around us contains heavy, slow-moving matter. Imagine an invisible ocean so still that you do not notice it directly. Different particles cross that ocean in different ways. Some move as if almost untouched. Others interact more strongly with the field, and that interaction becomes part of what we call their mass. A source thread behind the Higgs section is the difference between a nickname and a mechanism. The important point is not the famous nickname attached to the particle, but the way the Higgs field lets the theory describe certain particles as massive while preserving the deeper structure of the standard model. This picture is not the same as saying the Higgs field gives all mass to everything. Much of the mass of ordinary protons and neutrons comes from the energy of quarks and gluons bound together inside them. But the Higgs field is still essential, because it helps set the character of the elementary particles from which more complicated matter can be built. Here, the universe becomes strangely economical. The table, the air, the bones of planets, and the bright cores of stars all depend on a small family of fields and particles obeying rules that can be written in mathematics. The everyday world is not separate from the quantum world. It is what the quantum world looks like when its patterns become large, stable, and familiar. From there, Hypnos leads us softly toward quantum mechanics, where familiarity begins to loosen. The quantum world does not behave like tiny billiard balls moving through miniature rooms. It behaves through amplitudes, probabilities, and relationships that can be predicted with astonishing accuracy, even when they resist ordinary pictures. The double-slit experiment is a doorway into that strangeness. Send electrons one at a time toward a barrier with two openings, and the final pattern on a screen can build up like waves overlapping with one another. Yet each electron arrives as a small, localized event. It is as if the universe keeps a wider set of possibilities open until measurement gives one result. The point is not that nature is vague because our instruments are poor. Quantum theory places probability deep in the structure of the description itself. It does not merely hide a precise little story from us. It tells us that the story we can test is written in probabilities, and those probabilities are among the most successful predictions in all of science. This is why quantum mechanics feels both unsettling and dependable. It challenges the imagination, but it builds the devices of modern life. Semiconductors, lasers, medical imaging, atomic clocks, and the chemistry of matter all rest on the same quiet rules that seem strange when reduced to a single electron passing a pair of slits. The next discovery changes not the smallness of the world, but the stage on which everything happens. In ordinary life, space and time seem separate. Space is where things are. Time is when things happen. But relativity teaches that they are woven together into space-time, and that motion and gravity change how time is measured. Einstein's special relativity begins with a startling simplicity. The laws of physics should look the same for observers moving steadily relative to one another, and the speed of light in empty space is the same for all such observers. From those ideas comes a universe in which clocks and rulers are not absolute in the old sense. A source thread behind the quantum section is the double-slit experiment. In the final narration, that becomes a calm doorway into probability, interference, and measurement without preserving the interview phrasing or repeated caption fragments. If you were moving very fast past Earth, your clock would not agree with clocks left behind. The disagreement would not be a mechanical flaw or a trick of perception. It would be part of how space-time itself organizes events. Time is not a universal river flowing identically everywhere. It is more local, more intimate, and more connected to the path you take. General relativity deepens the story. Gravity is not merely a force pulling across empty space. Massive objects shape space-time, and objects follow the straightest available paths within that curved geometry. The Earth follows the Sun, not because it is attached by an invisible rope, but because space-time around the Sun has a particular shape. A useful image is a landscape without edges. A planet moves through that landscape, and the path that feels straight to the planet may look curved from far away. General relativity does not replace wonder with equations. It gives wonder a structure strong enough to predict bending starlight, shifting orbits, gravitational waves, and the slow ticking of clocks in different gravitational fields. Black holes are where this structure becomes most extreme. A black hole is not a cosmic drain with a surface you could stand on. It is a region where gravity has shaped space-time so severely that, beyond a boundary called the event horizon, future paths point inward. Even light cannot choose a route back out. For a distant observer, black holes are studied by their effects: stars moving around unseen mass, hot gas glowing before it falls inward, jets launched from violent environments, and the shadow-like silhouette formed by light bent around the compact object. The black hole itself remains defined by the geometry around it, not by a visible solid surface. Black holes also bring together the two great languages of modern physics. General relativity describes the smooth curvature of spacetime. Quantum theory describes the behavior of fields and particles. Near a black hole, both languages seem necessary, and that is why black holes remain so important. They are not just objects. They are questions made gravitational. Some physicists suspect that space-time may not be fundamental in the simplest way. It may emerge from deeper quantum relationships, like a smooth fabric appearing from threads too fine to see. This idea is not settled, but black holes give it a place to be tested in thought, mathematics, and observation. Now let the view widen. The same relativity that describes black holes also allowed scientists to imagine a changing universe. If space itself can stretch, then the galaxies are not simply flying through a fixed emptiness. The scale of space can grow, carrying distant galaxies farther from one another over cosmic time. Run that expansion backward in the mind, and the universe becomes denser and hotter. This is the root of the Big Bang model, not an explosion into pre-existing space, but an early hot, dense state from which space, matter, radiation, stars, and galaxies developed. A source thread behind the relativity section is the idea that Einstein's equations allowed more than one possible cosmic geometry. The narration uses that thread to move gently from spacetime to the possibility of an expanding universe. The idea was once difficult to accept. A universe with a beginning, or at least a hot early phase, felt less comfortable than a universe that had always existed in the same broad form. But observation slowly changed the map. Galaxies showed systematic redshifts. The cosmic microwave background revealed ancient radiation cooled by expansion. Light element abundances matched the physics of a young hot universe. One of the most beautiful images in cosmology is that old light. The cosmic microwave background is not a photograph of the Big Bang itself, but it is a relic from the time when the universe cooled enough for light to travel freely. It comes from every direction, a faint afterglow stretched into microwaves by the expansion of space. To imagine it, picture the whole observable universe once filled with a glowing fog. Matter and light were tangled together. As the universe expanded and cooled, atoms could form, and light was released into a cosmos that suddenly became transparent. That light has been traveling ever since, carrying a pattern of tiny temperature differences across the sky. Those tiny differences are not decorative. They are the early seeds of structure. Slightly denser regions pulled in more matter over time. Gravity amplified the faint pattern until galaxies, clusters, and great cosmic filaments could grow. The night sky is therefore not random glitter. It is the mature shape of small, early differences stretched across billions of years. Looking into space is also looking into time. The moon is seen as it was a little more than a second ago. The sun is seen as it was minutes ago. The Andromeda Galaxy is seen as it was millions of years ago. With distant galaxies, telescopes become time machines, receiving light that began its journey before Earth had familiar landscapes, oceans, or life. This does not mean the past is somewhere we can visit. It means that light has a travel time, and distance writes delay into every observation. Astronomy is the art of reading delayed messages with care. Every image of a remote galaxy is a fossil of light preserved by distance rather than stone. The Milky Way itself is one galaxy among many. It contains stars, gas, dust, dark matter, planets, stellar remnants, and a central supermassive black hole. From inside it, we see a pale band across the sky because we are looking through the disk of our own galaxy, like standing inside a city and seeing its lights in every direction. A source thread behind the cosmology section is Lemaitre's image of a beginning, sometimes described as a day without a yesterday. The narration keeps the poetic force of that idea while explaining the Big Bang as a hot, dense early state rather than an explosion into empty space. Beyond the Milky Way are other galaxies in shapes that feel almost architectural. Spirals with luminous arms, ellipticals like soft glowing clouds, irregular galaxies shaped by encounters, and clusters where hundreds or thousands of galaxies share the same broad gravitational environment. Galaxies also reveal one of the great unsolved discoveries: dark matter. Stars near the edges of many galaxies move too quickly to be explained by the visible matter alone. Clusters of galaxies bend light more strongly than their stars and gas can account for. The simplest broad explanation is that there is additional matter we do not see directly. Dark matter does not seem to shine, absorb, or scatter light in the usual way. It reveals itself through gravity. It helps form the scaffolding on which galaxies grow, shaping the cosmic web while remaining almost completely hidden from ordinary sight. The word dark can sound mysterious in a theatrical way, but in science it is often a humble word. It means not yet seen through light. Dark matter may be a new particle, or it may require a deeper revision of our ideas. But the evidence that something is missing from the visible inventory is strong and repeated across many scales. There is another cosmic puzzle beyond dark matter. The expansion of the universe appears to be accelerating, a discovery associated with observations of distant supernovae. The name dark energy is a placeholder for whatever drives that acceleration, or for the way our current theory accounts for it. It is one of the largest open questions in cosmology. Together, dark matter and dark energy remind us that success in science does not mean the universe has become small. The known laws explain an enormous amount, yet the largest accounting of the cosmos still contains deep unknowns. The map has become more accurate and also more mysterious. The search for life adds a quieter question to this cosmic map. The ingredients for planets are common. Many stars have worlds. Some planets may sit at distances where liquid water is possible under the right conditions. But habitability is not a single switch. It depends on atmosphere, chemistry, stability, geology, radiation, magnetic protection, and time. A source thread behind the dark matter section is the observation that galaxies rotate as if more gravitating matter is present than visible stars and gas can explain. The narration turns that into a quiet lesson about how gravity can reveal what light does not show. Earth may be ordinary in some materials and rare in its long continuity. Life here needed not only water and chemistry, but a long calm enough for complexity to unfold. A world can be promising for a moment and then lose its atmosphere, freeze, overheat, or be reshaped by its star. This is why the question of other civilizations is so gentle and so difficult. The galaxy is vast, and planets are numerous, yet technological life may require a chain of conditions that is fragile. The silence around us may be temporary, or it may be a clue that intelligence is uncommon, brief, hidden, or simply too far away for our present signals to meet. a calm mind can hold both possibilities. We may not be alone. We may be rare. Either way, the search changes how Earth appears. Our planet becomes not a background, but a living world in a vast experiment, a small blue answer to many conditions aligning at once. The discoveries we have followed tonight are not separate islands. The Higgs field belongs to the structure of matter. Quantum mechanics belongs to the behavior of particles and fields. Relativity belongs to spacetime and gravity. Cosmology belongs to the history of the whole observable universe. Dark matter and dark energy belong to what remains unfinished. And yet all of them meet in the same sky. A star shines because quantum rules and gravity allow nuclei to fuse. A galaxy forms because matter gathers in a universe shaped by expansion. A black hole tests the border between spacetime and quantum information. A telescope receives old light because the speed of light is finite and space has depth. Science at its best makes the universe feel both more knowable and more spacious. It replaces vague mystery with better mystery. It gives names to patterns, measures to distances, and equations to relationships, while leaving the night sky large enough for humility. As Hypnos guides us toward the end of this journey, imagine the universe as a quiet system of messages. Some are written in particles that live for fractions of moments. Some are written in galaxies turning over billions of years. Some are written in the ancient glow that arrives from every direction. Some are written in what we cannot yet see. The discoveries do not end the wonder. They deepen it. Matter has hidden fields. Empty space has structure. Time bends. Light carries history. Galaxies move as if held by invisible mass. The universe expands with a story still unfolding. And somewhere inside that story, on a small planet around an ordinary star, a mind can look upward and ask how any of it is possible. That question is part of the universe too. Matter becoming curious about matter, starlight becoming thought, the cosmos learning to read a little of its own handwriting. To understand why the Higgs discovery mattered so much, it helps to remember that physics is not only a catalog of things. It is also a search for symmetry. A symmetry is a sameness hidden beneath change. The laws may keep their form even when a system moves, turns, or shifts from one description to another. The standard model of particle physics is built from this disciplined symmetry. It does not feel simple when first encountered, but its success comes from a precise architecture. Particles are not loose beads in empty space. They are excitations of fields, and the fields are tied together by rules about how nature may transform without changing its deepest behavior. The difficulty was that some particles clearly behave as if they have mass, while the mathematical symmetries needed by the theory seem to prefer massless force carriers. The Higgs mechanism offered a way for mass to appear without simply breaking the whole structure apart. It allowed the universe to keep the elegance of the rules while still making the heavy, textured world we know. This is why a particle collider can feel almost mythic while remaining intensely practical. Inside the Large Hadron Collider, protons are accelerated and guided around a ring, then brought into collision. The goal is not to smash matter like pottery, but to concentrate energy so that rare field excitations can appear briefly and leave measurable traces. The detectors surrounding those collisions are enormous instruments of patience. Layers of sensors record paths, energies, and decay products. No single collision announces the discovery by itself. Instead, physicists gather statistics, compare patterns with predictions, and ask whether the signal rises above the noise with enough strength to trust. There is something sleep-friendly in that patience. The universe does not always speak in one clear sentence. Sometimes it speaks through billions of small events, and understanding means letting the pattern slowly separate from the background. Quantum mechanics adds a second lesson in humility. It tells us that the world is not obliged to match the images our brains evolved to handle. We are good at stones, trees, water, tools, and footsteps. We are less naturally prepared for wave functions, superposition, measurement, and entanglement. Yet the quantum world is not a fantasy world. It is exact enough to build clocks that lose almost no time, circuits that guide information through a computer, and lasers that keep their light orderly. Its strangeness is not a failure of science. It is a sign that the universe is deeper than our everyday metaphors. A single electron in the double-slit experiment is not a tiny marble choosing one doorway in the familiar sense. The mathematical description allows alternatives to combine. Where possibilities reinforce, detections become more likely. Where they cancel, detections become rare. Over time, the screen records a pattern that looks like wave interference, even though each mark arrives one by one. This is why the experiment remains so famous. It is small enough to describe in a few sentences, but large enough in meaning to unsettle an entire worldview. It asks us to accept that prediction may be precise even when the underlying picture is not the simple picture we wanted. Relativity offers a different quiet revolution. It begins by taking light seriously. If the speed of light is the same for steadily moving observers, then space and time must adjust. What seemed fixed becomes relational. Events that look simultaneous from one viewpoint need not be simultaneous from another. This does not make reality arbitrary. It makes reality geometric. The interval through space-time becomes the deeper quantity, while measurements of distance and duration depend on the observer's path. The universe keeps order, but the order is more subtle than the old separation between space and time. General relativity then turns gravity into geometry. A clock closer to a massive body ticks differently from a clock farther away. Light passing near a massive object follows a curved route. The orbit of Mercury carries a small extra shift that Newton's theory could not fully explain. These are not poetic effects. They are measured facts. Even navigation satellites must respect relativity. Their clocks experience different gravitational and motion effects than clocks on Earth's surface. The corrections are small by human standards, but large enough that modern positioning would drift without them. Cosmic ideas quietly enter ordinary maps. Black holes are the place where the corrections become destiny. Near the event horizon, the geometry of space-time is so extreme that escape routes vanish. From far away, infalling matter can appear to slow and redden. From the matter's own local experience, the journey inward has its own finite path. No human observer has traveled there, but the evidence around black holes is rich. Stars near the center of the Milky Way loop around an unseen compact mass. Merging black holes shake space-time itself, sending gravitational waves across the universe. Hot material near supermassive black holes can outshine whole galaxies. The first images of black hole shadows did not show a surface. They showed light from hot surrounding material bent by gravity into a ring-like structure around a central darkness. That darkness was not empty in the ordinary sense. It was the visual consequence of paths light could not take back to us. When black holes merge, they convert part of their mass into ripples of space-time. These gravitational waves stretch and squeeze distances by unimaginably tiny amounts as they pass. Detecting them required instruments so sensitive that they could measure changes far smaller than the width of a proton over kilometer-long arms. The detection of gravitational waves opened another sense for astronomy. Telescopes listen with light. Gravitational wave detectors listen with geometry. Together, they let us study events that may be dark, hidden, or too violent for ordinary images to tell the whole story. Cosmology carries the same patience onto the largest scale. The Big Bang model is sometimes misunderstood as a blast from a single point into surrounding emptiness. A calmer picture is that space itself was once hotter and denser everywhere, and that the distances between faraway regions grew as the universe expanded. The expansion of space does not mean every object expands. Atoms, people, planets, stars, and galaxies are held together by local forces. The expansion becomes visible across enormous cosmic distances, where the average separation between unbound galaxies increases over time. The cosmic microwave background gives this picture a luminous anchor. Its tiny variations are mapped across the whole sky, and those variations match a universe that began hot, dense, and nearly uniform, with slight differences that gravity could later amplify into structure. Those slight differences are breathtaking because they connect the early universe to the present one. A faint ripple in ancient radiation becomes, through billions of years of gravity, a cluster of galaxies. A small unevenness becomes a place where stars can form, metals can be forged, planets can condense, and eventually minds can wonder. The first stars changed the universe in another way. Before them, the cosmos was mostly hydrogen, helium, and traces of lighter elements. Inside stars, nuclear fusion built heavier nuclei. In stellar deaths, supernovae and other violent events scattered enriched material into space. The chemistry of planets and bodies is therefore a later chapter in a stellar story. The iron in blood, the calcium in bone, the oxygen in water, and the silicon in rock all belong to cosmic history. They were not present in the same abundance at the beginning. They were made, processed, and dispersed by generations of stars. This makes the universe feel less like a distant spectacle and more like a genealogy. The night sky is not only something above us, it is part of the ancestry of everything familiar. The atoms of the body are old travelers, assembled into a temporary form that can look back at the stars. Galaxies are the great cities of that ancestry. They gather gas, stars, dust, planets, black holes, and dark matter into long-lived structures. Some galaxies grow quietly. Others collide and merge, stretching tidal tails across space and triggering new waves of star formation. The Milky Way and Andromeda are moving toward a future encounter on a timescale far beyond human history. By then, the night sky would be transformed, though individual stars are so widely spaced that direct stellar collisions would be rare. Gravity would rearrange the architecture more than it would smash stars together. Dark matter is woven through this galactic story. In simulations, visible matter falls into dark matter halos, cooling into disks and forming stars. Without dark matter, the timing and structure of galaxy formation would look very different from what we observe. The mystery is that dark matter has weight without ordinary light. It bends paths, holds galaxies, and shapes clusters, yet it does not shine in telescopes the way stars do. It is a reminder that seeing is not the only form of knowing. Gravity can reveal what light does not show. Dark energy is even more abstract. It is not a cloud we can photograph or a particle we have isolated. It is a name attached to the observed acceleration of cosmic expansion. The name may one day be replaced by a deeper theory, but for now, it marks a real gap in our understanding. This gap is not embarrassing. It is alive. The most mature sciences are not the ones with no unknowns. They are the ones that can point clearly to what they do not yet understand and build instruments, theories, and observations around that honest boundary. The search for life belongs at that boundary too. Telescopes can measure starlight filtered through exoplanet atmospheres. They can estimate sizes, masses, orbits, and temperatures. They can look for molecules that might, under careful interpretation, hint at chemistry worth studying further. But life is not announced by a single easy sign. Oxygen can have non-biological sources under some conditions. Methane can arise in several ways. Water is necessary for Earth-like life, but it is not enough by itself. Context matters. A biosignature is a conversation among many clues. That carefulness is part of the beauty. The question of life elsewhere deserves wonder, but it also deserves restraint. The universe is large enough for hope and complex enough for patience. In the same way, the Fermi question is not a single answer waiting on a shelf. If planets are common, where is everyone? Perhaps civilizations are rare. Perhaps they are brief. Perhaps distances are too large. Perhaps signals are hard to recognize. Perhaps the galaxy is full of quiet or full of life that does not speak in ways we can hear. Each possibility changes the emotional shape of the sky. A crowded universe would make Earth one voice in a vast chorus. A lonely universe would make Earth precious in another way, a fragile place where matter woke up at least once. What remains constant is responsibility. The more we learn about cosmic scale, the more specific home becomes. A pale planet with oceans, weather, soil, microbes, forests, cities, and memory is not made ordinary by the size of the universe. It is made more delicate. The grand discoveries of physics and astronomy do not ask us to feel small in a hopeless way. They ask us to feel accurately placed. We are small in size, brief in time, and yet connected by atoms, light, gravity, and thought to the largest story we can observe. That is the calm paradox at the center of cosmic discovery. The universe is older and larger than intuition can hold, but it is not closed to understanding. A human mind, with mathematics and instruments, can reach from a laboratory signal to the early universe, from a falling apple to a black hole, from a spectral line to the chemistry of stars. For now, the sky can return to being quiet. The questions can remain open without needing to be solved all at once. The particles, fields, galaxies, and old light continue their patient work, far beyond the window, far beyond the edge of ordinary sleep.